Alright guys, we're going to go ahead and look at the worksheet that I gave you today on rotational acceleration and practice some of those problems. Number 8, I assume you have the worksheet in front of you. Number 8 says to throw a discus, the thrower holds it with a fully outstretched arm starting from rest. Now the from rest part is very important. It tells us that our initial velocity is 0 radians per second, and this is an angular velocity. That's why I wrote omega. We're talking about something rotating. Let's see, starting from rest, he begins to turn with a constant angular acceleration, releasing the discus after making one complete revolution. So we know our angular displacement is 1 revolution, or that's equal to 2 pi radians, and we want to make sure that we're dealing with radians as we do these problems. The diameter of the circle is 1.8 meters. Now that's only important because the radius pops up in a couple of my equations. So now I can figure out my radius by doing 1.8 meters divided by 2. So my radius is 0.9 meters. If the thrower takes 1 second to complete the 1 revolution starting from rest, what will be the speed of the discus at release? Now it did not say what would be the angular speed of the discus, so it did not ask for our final omega. What it did ask for was our final linear speed, or the linear speed as soon as the object is released. Now from my equations I know that linear speed is related to omega by the radius. So I can assume that if I find my final omega, then I'll be able to use this equation and find my linear speed. That's the overall goal here. There's one key point of information that I did not write down, and that is I know time is equal to 1 second. Alright, so from here, a couple of different ways to do this. One easy way that we saw in class was to use the average velocity equation, where that equals delta theta over time, and that in turn is equal to your initial angular velocity plus your final angular velocity over 2. It's a mathematical average. So I have everything I need besides our final omega. So I'm going to substitute now. 2 pi radians over 1 second equal to omega f over 2. So when I solve here, if I multiply both sides by 2, then my final angular velocity is 4 pi radians. Now from here, to get my linear speed, I'm going to do v equals r omega, so v equals 0.9 times omega, which is 4 pi. You should get about 11 meters per second. Okay, so for number 9, it's talking about a computer disk starting from rest. So again, my initial angular velocity is 0 radians per second. It says it has an angular acceleration of 190 radians per second squared, or per second, and it only accelerates until it reaches a final speed, angular speed, of 7,200 revolutions per minute. Now if we take that 7,200 and we want to go ahead and convert that, I'm going to multiply that by 2 pi over 60 to get 754 radians per second, so that I'm using the correct units now. Okay, it says how many revolutions has the disk made 10 seconds after it starts up? Now in class we said, well, there's going to be 2 parts to this problem. The first part is we got to figure out how much time it's accelerating, because we're going to have a total of 10 seconds. And then the next part, it's going to go at this constant speed of 754 radians per second. So first I'm going to figure out the time here. I'm going to use this equation. Alpha equals omega final minus omega initial over t. So I will know how long it's actually accelerating. And then from there, I'll be able to use like a delta x equation or something to find delta x. Now, some of you might ask, like, why do we need to find time? I have to know time here so that I know how long it's actually moving at the constant speed for the second part of the problem. So 190 equals 754 over t. If I multiply both sides by t and then divide by 190, I will get a time of about 4 seconds. Okay, now that means that there are 6 seconds left over here for part 2. I'm just going to go ahead and write t2 equals 6 seconds. I'm still not done with part 1. I have to figure out how far we go, or our angular displacement in those 4 seconds. And I'm just going to use this equation. Since my initial omega is 0, I can really just cross that out. So 1/2 times 190 times 4 squared, that will give me a delta theta of about 1520 radians. Okay, now for the second part, we have 6 seconds left, and here is where it's moving at a constant angular speed. So I'm going to use just a angular speed equation, and let's see, omega equals delta theta over t when you're moving at a constant speed, because our average becomes the speed at every point in time. So since I know my time and I know my omega, it's going to be no problem to solve for theta. So delta theta for this part will be 754 times 6, or delta theta is going to equal about 4,524 radians. From there, the problem is asking for a total, well, how many revolutions. So first off, I need to add these together from these two parts to get the total angular displacement. Divide that by 2 pi, and then I'll have my number of revolutions. So if I add those together, so I'm going to do theta 1 plus theta 2, you get about 6044. Now that is radians. I want that in revolutions, so I need to divide by 2 pi radians per revolution. Be careful when you do this in your calculator that you're not dividing by 2 and then multiplying by pi. So in your calculator, you probably want to make sure that's in parentheses. That's a pretty common mistake. And then we will get about 960 approximately. You might get a little off in the grand scheme of things when we're talking about a number close to 1,000. That's fine. And revolutions should be your answer. Okay, number 10. The crankshaft in a race car goes from rest to 3,000 RPMs in 2 seconds. So just out of that sentence, I'm going to say my initial angular velocity is 0 from rest. My final is going to be 3,000 R revs per minute. I need to multiply that by 2 pi over 60 to get our angular velocity in radians per second. And that comes out to be about 314 radians per second. The time that it takes to reach that velocity is 2 seconds. What is the crankshaft's angular acceleration? So because I have omega f, omega I, and t, I know that alpha equals your final rotational speed minus your initial rotational speed over time. So I'm just going to plug the numbers in here. So 314 minus 0 over 2. So alpha then equals 157 radians per second per second. Now the second part says how many revolutions has the disk, whoa, that's number 9, I'm sorry. Part B says how many revolutions does it make while reaching this speed. So now it's basically just asking for theta. And you can use a couple different equations to figure that out. I'm going to use the delta theta equation, this 1/2 alpha t squared plus omega I t. The reason I'm using this is because theta is already solved for me. I don't have to do any algebra there. So delta theta, please remember if you're going to use delta theta over time, that gives you an average omega. It does not give you the final or initial. Okay, so you can't just do delta theta over t and come up with the right answer. Unless you use it appropriately, in which you'd have to like multiply the average by 2. Anyways, 1/2, 157 times t squared times 2. Now my initial omega is 0, so that term completely goes away. So we're left with delta theta for part B equals 314 radians. Well, that's convenient. That's just a coincidence there. Here for number 11, I went ahead and wrote my known variables. The problem tells me that we start at 14 radians per second, we end at 22 radians per second, and it's basically just asking for alpha. So I'm going to use the equation alpha equals omega final minus omega initial over time. So alpha then equals 22 minus 14 over 5 seconds, and that should give you about 1.6 radians per second per second. Okay, number 12, I went ahead and did the same thing. I looked at our problem and it says suppose you have something spinning at 27 radians per second and then it goes to 6 radians per second. And so there's our initial and final omegas. And then it says it does that over a period of 2.3 seconds and find your acceleration. Again, we can use this equation. Please don't get these out of order. It will mess with the sign of your answer. And if you get the wrong sign for your answer, then we don't have enough information about the motion. We don't know if it's moving counterclockwise or clockwise. In this case, it is slowing down in a counterclockwise direction, so we should get a negative acceleration or a clockwise acceleration. So I'm just going to plug our numbers in. 27 minus 6 over 2.3 equals alpha. So alpha should be negative 9.1 radians per second per second. I don't know what that is. Okay, 13 says a disk is accelerated from rest. That tells me my initial velocity is 0, angular velocity is 0. At a rate of 4.3 radians per second, just based on those units, radians per second, I know that that is my acceleration, angular acceleration. And it says we do that for 12 seconds. And it's asking us to find our final omega. Now this is nice. Again, we're going to use the same equation. We're just going to have to rearrange some variables a little bit. So your final omega is going to equal acceleration times time. We're going to multiply both sides by t and then add our initial velocity. Now our initial velocity is 0. That term is going to go away. So omega f ends up being our acceleration, which is 4.3, times our time, which is 12. So omega f equals 52 radians per second. Okay, 14. A wheel rotates with a constant angular velocity of 34 radians per second for a period of 12 seconds. What is the final angular displacement? So actually there's no acceleration here because it says constant angular velocity. So I'm just going to write omegas. There's not going to be an initial or final. Omega is 34 radians per second. It gives me a time of 12 seconds and it asks me to find a displacement. So, well, I know that when we're moving at a constant speed, displacement divided by time is going to equal that omega. So I'm just going to say theta then is equal to omega times time, which is going to be 34 times 12. That should give us 408 radians. So delta theta equals 408 radians. And here it doesn't say turn to revolutions or anything. 15. The disk in a computer disk drive spins up from rest, so omega I equals 0 radians per second, to a final angular speed of 5400. So omega F is 5400 revs per minute. I'm automatically going to change that to radians per second by multiplying by 2 pi over 60. That gives me 565 radians per second. And let's see, a time is given 2 seconds. Now the first question was the angular acceleration of the disk. Guys, again and again we've seen omega I, omega F, t, and it's asking for angular acceleration. I'm going to use this equation. So alpha is going to be 565 minus 0 over 2. So I will get about 283 radians per second squared, or per second per second. At the end of 2 seconds, how many revolutions has the disk made? So now it's just asking for theta. Theta, I'm going to use this equation. You could probably use another one with theta in it and get the same answer. I'm sure you could. But this one I don't have to do any rearranging in my algebra. That's why I like it. 283 is alpha, t is 2. Don't forget to square it. You'll get a delta theta of 90 revolutions. Alright, so here we have a graph for number 16. It says, the graph below shows the angular velocity for a propeller of a ship. A, describe the motion of the propeller. Well, first of all, we're approaching 0 radians per second. That must mean that we are slowing down. Now, because my omega, my angular speed, is negative, that indicates a direction. And if you remember, when we first started rotational motion, we said that negative was a clockwise rotation. So it must be slowing down clockwise. And then from there, from 4 seconds to 8 seconds, it's leaving 0 radians per second. So now it's speeding up in a positive direction, or when we're talking about rotation, we would say counterclockwise, because positive is counterclockwise. And then finally, we continue at a constant speed, angular speed, counterclockwise. Again, it's going to be positive. Now B says draw the angular acceleration graph for the propeller. So this is pretty simple. We know if we have an omega in time graph or an angular velocity in time graph, then we can find our acceleration by looking at the slope. So if I look at the slope of this, I'm going 4 radians per second for every 4 seconds, or it looks like my alpha is going to be just 1 radian per second per second. And that lasts for 8 seconds. And then after that, I don't have any acceleration. So, oh crap, can I not do math? No, I can't do math. Sorry. This is 8 to 0, so this should be 8. Not 4. Okay, that's 8 radians per second in 4 seconds. So that makes our acceleration 2. Sorry. So that means that, let's see, if I were to draw an alpha graph, radians per second, and we have time over here. I'm going to do the same scale here. Let's see, 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. And then 1. So I know for the first 8 seconds, I accelerate at 2 radians per second. And then from 8 seconds to 12 seconds, I have 0 acceleration. So your acceleration and time graph should look something like this. Alright, that's everything on the video. Sorry it took me a long time. I hope it's helpful. Good luck studying.